Let's discuss about product of two vectors. Now, whenever we talk about product of two vectors, there are two types. Okay, one is called a dot product or scalar product. One more is called cross product or vector product. Now, we'll discuss these two in detail. Now, in this particular video, we are going to discuss about the dot product, or you can also call it as a scalar product. Okay, scalar product of two vectors. Now, what we mean by a scalar product or a dot product? Now, here, this you have already discussed about these things and you have learnt about these things. Now, whenever we talk about a dot product, the first thing is between the two vectors, we calculate the magnitude of the product between the two vectors, right? That is basically dot product, or that's why we call this as a scalar product. In the sense, suppose say we have vector A, which is equal to ax I cap plus ay j cap plus az k cap, and let's say vector B is equal to bx I cap plus by j cap plus bz k cap. Let's say you have two vectors A and B. Now the dot product between these two vectors is defined as vector A dot vector B is equal to mod of A into mod of B into cos theta. This is basically how we define the dot product. Now theta is the angle between the two vectors, vector A and vector B. In the sense, suppose say if this is vector A, say this is vector B. The angle between them is theta. That theta is basically cos of that angle theta is what we take or what we consider here. Fair enough? Now this is how a dot product is defined. Okay. Now there are certain observations what we have to do here in the dot product. Okay, very important observations these are, because most of the times whenever you are solving a problem, these observations come in handy. All right. Now let's discuss about these observations, or you can say more like properties, characteristics of dot product. That's how we can say. Now when it comes to the dot product, the very first observation what we have is that dot product is a scalar quantity. The name itself tells, right? So only magnitude. If you have vector A dot vector B, the result is going to be just a number without any direction whatsoever. Because whenever we talk about a vector, we also need to have a direction, isn't it? But the dot product will not have a direction. It's just a scalar quantity. First observation, or you can say characteristic also. Fine. The second one, suppose let's say vector A is a non-zero quantity, or you can say mod of vector A is non-zero and mod of vector B is also non-zero. Whereas let's say vector A dot vector B is 0. Then what we say is that the angle between vector A and vector B is 90 degree. In other words, we can also confirm that vector A is perpendicular to vector B. Perpendicular. The reason is cos 90 has to be 0. They are called as orthogonal vectors. Okay, let me repeat this again. If A and B are non-zero vectors, but the dot product is 0, then we can confirm that the angle between the two vectors is 90 degree. Or you can also say that vector A and vector B are orthogonal vectors. Orthogonal vectors. That means they are 90 degree. Okay. This is the second observation. Third observation is that suppose let's say theta is equal to 0 degree. Okay. Assume that theta is 0 degree. Now the see, if the angle is 0 degree, they are collinear, correct? Or either they are parallel or they are collinear, isn't it? That means in this case, the product of the two vectors, the dot product between the two vectors is going to be maximum. In the sense, here vector A dot vector B is equal to mod of A into mod of B, maximum value. Suppose if you are taking the same vector, then vector A dot vector A is equal to mod of A whole square. The maximum magnitude of the dot product is when the angle is going to be 0 degree. That means they are parallel to each other. Fair enough? Now, the next observation is, suppose if theta becomes 180 degree. That means they are anti-parallel. See, in the first case here, you have one vector like this, one more vector like this. They are parallel to each other. See, in the next one vector is like this, and one more vector in the opposite direction. See, like this. Now what we tell is the angle is 180. See, this angle is 180 degree and cos 180 is -1. So what we get is vector A dot vector B becomes minus mod of A into mod of B. Now in physics we use this a lot, correct? Whenever we talk about angle between the two vectors, 0, 90, 180, we take different cases. Now this is what it is, because whenever we take the dot product, cos 180 is -1. This is the fourth observation. Let's look into the next observation. See, the next observation, that is the fifth observation. Suppose say you have a vector and you resolve it into components. How exactly the product is going to become? See here, the fifth one. Suppose say vector A, AX I cap, AY J cap, AZ K cap, and vector B, BX I cap, BY J cap, BZ K cap. Now, whenever we do the dot product between vector A and vector B, fine. Now, since we have resolved this into components, there is no angle theta whatsoever, correct? See, theta comes only whenever we are taking the two vectors as it is. When you resolve that vector, for example, say this is my vector and I resolve it into its components x, y, and z. Okay, and you have another vector. So let's assume that you have another vector. This is one vector, this is one more. Suppose say if two of them are like this. This you resolve into components, this you resolve into components. Now what's going to happen? We have parallel and perpendicular vectors, isn't it? There is no concept of angle theta when you resolve the vector into its components. Fine. So now since we have resolved it, whenever we take vector A dot vector B, in this case, when you take vector A dot vector B, then see, we multiply normally, but then the result is going to be just AX BX plus AY BY plus AZ BZ. Now, the reason why we don't get AX BY, AX and BZ, something like this, the reason is, if you look at it, I dot J, this is going to become 0. Think about it, they're 90 degree, correct? So in this case, it's like this one. So when you look at it, you have X, Y, and Z, three values or three axes, you can say. So along the X axis, Y axis, and Z axis, when you have three, the angle between these two is 90. So when you have cos 90, it's 0. So I dot J becomes 0. Same way, J dot K. See, this angle is 90 degree. So J dot K is also 90. Same way, I dot K, this is also 90 degree. That means whenever we look at the dot product between the perpendicular axis, that is I dot J is equal to 0. This is also equal to J dot K, which is also equal to K dot I. K dot I. Fair enough? So this value is going to be 0. That's why whenever we multiply the two vectors in its component form, we are going to get this as the formula. Clear? This is another observation. What if we want the angle between the two vectors? That is the next observation or characteristic what we can say is that, suppose say you have vector A dot vector B. This is what? Mod of A into mod of B into cos theta. Correct? So cos theta is equal to vector A dot vector B over mod of A into mod of B. This is the angle. This is how you find the angle between the two vectors. Alright. So these are like 6 observations what we can think of in the dot product between the two vectors. Now there are certain properties, basically distributive and commutative. We'll look into these two now. Okay, so more like two laws which the dot product of two vectors is going to satisfy. Now, when we talk about commutative law, that is, so this all of you know what it is, correct? So in the first one, we look at commutative law. So commutative law talks about vector A dot vector B is equal to vector B dot vector A. You can think about it like this. Vector A dot vector B is mod of A into mod of B to cos theta. Correct? Now look at this one. Suppose say this is A and this is B. Assume that this is A, assume that this is B. This is angle theta. When we take A dot B, we take mod of A, mod of B cos theta. Theta is the angle between them. Now when you take B dot A, we can write this as mod of B into mod of A into cos theta, because the value of theta, this theta remains the same, isn't it? This is also theta, this is also theta. There is no difference whatsoever. That's why vector A dot B and vector B dot A, we can expand it like this. Now, we know that cos theta value is the same. And we also know that multiplication of two numbers is commutative, correct? Multiplication is closed under commutative law. So, A dot B should be equal to B dot A. So, what can we confirm? We can confirm that A dot B is equal to B dot A. That's the proof what we can tell that this vector product of two vectors, especially the dot product, is commutative in nature. Clear? The next one, the next law you can say is the distributive law. Okay, so this we are looking at distributive law. Now in this case what we have is, suppose if you have vector A plus vector B dot vector C, you're looking at both. This becomes vector A dot vector C plus vector B dot vector C. Okay, so we get both A dot C plus B dot C. So this is distributive law of addition over the dot product. Multiplication you can call it. Fine. So this holds good. But you can't do A dot C plus B is equal to A plus B dot. No, that is not possible. This is possible. Clear? Now the third one, the third law you can say is multiplying by a constant. Okay, suppose say your so this you can say is multiplying or multiplication by a constant. Okay, now what we have, suppose if you have lambda, some constant lambda into A dot B, this is equal to lambda into A dot B, or this can also be written as lambda into, oh, this lambda into A dot B, it's already done. You can also write this as lambda B dot A or lambda into B dot A. They're all the same. Basically, whenever you're multiplying by a constant, you can interchange the constant to whichever vector you want or however you want. Clear? So these are the three properties which, the vector product of the two vectors, they satisfy. Clear? Now, in the next video, we'll look into one of the important, you can say, applications of this dot product, which is the projection of one vector over the another.